Southampton's main tasks are to produce the research on the electrodes, so the anodes and the cathode that could help to promote the two reactions.
We are in charge of the development of the cathode electrode, which reduces the carbon dioxide, and the anode electrode that oxidizes the water to produce hydrogen peroxide. The production of carbon dioxide produces ethylene, and together with hydrogen peroxide from the other electrode produces ethylene oxide, which is the main product we're going to produce in this project as a proof of concept.
We're producing the technologies or doing the research to develop new catalyst and electrode designs.
Southampton has several roles. One is the testing of the catalyst for the reduction of carbon dioxide in something that we call the gas diffusion electrode. The gas diffusion electrode is basically a membrane where one side is gas and then the other side is liquid, and the gas side is CO2 that diffuses through the pores of the gas diffusion electrode and converts it into ethylene.
The reaction we're looking at for converting carbon dioxide into ethylene, whenever you see this done in any system, it's always using a copper electrode. So copper is very special because it is the only material we know of that can make very large amounts of what we call C2 materials. So that's basically a carbon dioxide reduction product with two carbons that are bonded to each other. When we think about the key step in carbon dioxide reduction to ethylene, it's the formation of that carbon-to-carbon bond, which is absolutely key in making sure we have that very high yield. So the biggest challenge we have is getting large amounts of that carbon-to-carbon bond to occur. So one of the things that we've been looking at is various different coatings we can put onto the surface of the copper particles we're using. One of the things we've been working with is a porous polymer coating. So the idea is you have a very thin porous layer over the top of the particles. Those pores are so small that they stop bubbles forming. So what that means is when your carbon dioxide gas gets trapped in there, it doesn't form bubbles, it gets trapped in very high concentrations, and that means that you can get a fast rate of reaction at the catalyst surface. So it's kind of artificially giving you a very high level of carbon dioxide, which then gives you a very high rate of reaction. The thickness of the polymer layer is on the order of a few tens of nanometers, and then the pores are around the nanometer size as well. So it's 10 to the minus 9, so 1,000th of a millionth of a meter. The first part of the role is looking at these manufactured copper gas diffusion electrodes and just trying to work out which the best manufacturing technique is. And that means we can then feed back to our partners and say, based on these analysis of all of these different conditions, we believe that when you want to do your experiments on your much larger setup, you should focus on these 3 or these 5, which look to be the most promising.
On the other hand, SOTON is working on the anode side in the other part of the electrochemical cell, and we have proposed a bottom-up diamond electrode.
We had a breakthrough with especially the hydrogen peroxide production, and we found that the BDD is performed extremely well. SOTON has done a fantastic job in terms of screening the different types.
And so we happen to have some lying around in the lab from 2012. So I thought, let's just try this stuff and see how it works. And it was great. And it produced hydrogen peroxide, and it produced a lot of hydrogen peroxide. And it's also a very stable catalyst. You can use the same electrode over and over and over again. So what my research now is focused on is trying to identify the optimal level of boron that we need to add to the boron-doped diamond to get the most hydrogen peroxide. Because like with all things, if you add too little, not that good. If you add too much, not that good. So you need to do it in moderation, right? We found that boron-doped diamond is a very suitable catalyst for this reaction and this project, and it meets all of the requirements more or less that were set to us for the water oxidation part. that was more of the step forward that I was proud of. Not only found a material that meets the requirements for the project, but that we were able to show that we can actually get this reaction to work at the level that we wanted to work, at the performance. That was the cool thing.